Hello everyone, we will continue with our lecture series. Last lecture we have seen solution of linear system, especially LTI system, linear time invariant systems. So, we will continue our discussion further in this lecture. We will study something, we will use those solutions what we derived last class to study the properties of like stability, controllability and observability of linear systems. When I tell linear systems, in this particular course we will confine ourselves to LTI systems actually. And before I proceed further, also remember that stability, controllability and observability are three different properties of linear system. They are nothing related to each other in a way. In other words, if a system is unstable, it can still be controllable and it can still be observable. Okay. The system is probably like not observable, it can still be stable and things like that actually. Okay. So, just remember there are three independent properties and they are very much useful before you design controller or observer actually. So, let us study that in detail. So, first we will study the stability, then we will study controllability and towards the end of this lecture we will study observability. So, stability of linear time invariant system. So, first of all what we mean by stability? We all know that a system, when you talk about stability, we normally talk about stability of equilibrium points. Okay. So, if the system is, if a system in equilibrium is disturbed and the system returns back to the equilibrium point with time, then the equilibrium is said to be stable. We all probably know this actually. Pictorially speaking, if this kind of a thing happens, then the ball is at rest. Here also ball is at rest theoretically, but the moment you disturb a little bit here, it will never come back, whereas if you disturb a little bit here, then it is supposed to come back and stabilize here. So, these are all very standard concepts that you have, it is very clear to us actually. However, also remember that when we discuss about stability of nonlinear systems, things need not be as simple as that. There are various notions of stability and we will study those in detail when we talk about Lyapunov stability theory. Okay. But in linear systems, system is kind of either stable or unstable. There may be a very borderline case which is marginally stable and all that. So, in other words, if you assume like a flat surface here, then the ball if you just keeps on rolling, it will stabilize wherever it goes actually. So, that's a concept of marginal stability. And normally we visualize the system is either stable or unstable actually. Okay. So, let us see how this concept is tied up mathematically actually. So, what we discuss here is that we have a system x dot equal to x also. Okay, this also tells us that stability is nothing to do with plus BU part. And when we talk about system stability, we normally talk about homogeneous system. That is the stability behavior actually. So, BU plus Ax plus BU, that BU part is the forcing function part, that is something to do with controllability of the system, but not stability actually. So, when you call that system is naturally stable, that means we have to analyze only the x part of it, x dot equal to x, and if it is a nonlinear system, it will be x dot equal to f of x actually. So, control input typically will not study as part of the natural stability of the system actually. Anyway, coming back, we know this is the system dynamics, okay, and this is initial condition x of 0 is x 0. Now, the question is, can we conclude about the nature of the solution without actually solving the system model? We already have it, okay, but we all want to know the solution nature. We are not interested in that particular solution, starting from this particular initial condition, what will happen and things like that. But we just want to know the stability nature of the system. In other words, the nature of the solution, will it ever converge to 0 or will it go to infinity? That is the study actually. And also remember that when you discuss x dot equal to x, these are normally delta x dot equal to a times delta x, that is what the linearization theory actually. Okay. So, when you discuss stability of linear system especially, the aim here is to take delta x to 0, okay, that means x has to go to 0. So, the question that you are asking is, will this solution starting from this initial condition, whatever may be the initial condition x 0 here, will it go to 0 or will it go to infinity actually? There are two questions that you are asking as part of the stability analysis, and the answer fortunately turns out to be yes, and it all has to do with the poles of the system, and the poles by definition are nothing but the eigenvalues of the matrix. Okay. So, if you just know the A matrix, which is we are assuming it is a time invariant matrix, obviously it is like a constant matrix actually. So, we can evaluate the eigenvalues, and the system stability nature is all hidden in the eigenvalues of the matrix actually. And these are all also called poles of the system. They are actually, if you take this input output relationship and things like that, when you do this Laplace transform, convert it to transfer function method, I mean in the state space to transfer function, then you see that the determinant of Si minus A will come in the denominator. Okay. So, that is how this poles and all will be defined actually that way. So, eigenvalues of A are nothing but poles of the system, and the nature of the solution is primarily governed by the location of the poles. We will see how it is there and things like that. Before we do that, we just recall there was a matrix transformation that we discussed some time back in one of the previous lectures. The various transformations are possible in a matrix, and normally when you have this kind of a system, x is n dimensional and x dot is also n dimensional. X dot is term by term differentiation, that is by definition. So, this is also n by 1, that is also n by 1. So, obviously, A has to be n by n. So, it is certainly a square matrix actually. The plus Bu, that B matrix need not be square matrix, but A is certainly a square matrix. So, if you see this table, we are not typically interested in this non-square part of it, we are interested in square part of it. Okay. Now, this square matrix may or may not be symmetric. Okay. And if it is, I mean in this linear system analysis, it need not be symmetric either. I mean we are not assuming anything here. However, you can also see that if it is a symmetric matrix, it can have independent eigenvalue vectors. It may not have independent independent eigenvectors. So, in general, okay. So, it is like you can reduce a symmetric matrix to diagonal form by similarity transformation, okay. And it can be done for the Jordan. I mean, if it does not have this n independent eigenvectors, it can reduce it to like Jordan form. And the matrix need not be really symmetric to do that. We can start with any matrix and then carry on with that actually. But if it is symmetric, it has two possibilities. That is all this table tells actually. But in general, any square matrix you can really reduce it to like either a diagonal form or a Jordan form by carrying out similarity transformation. And how do you do similarity transformation? Like given an A matrix n by n, you can construct this n by n matrix P, which is supposed to be non-singular, such that this P inverse A P is nothing but B matrix, and then this n B matrices are supposed to be similar actually. So, what are the two forms? Either it is diagonal or it is Jordan. Okay. So, if there are n linearly independent eigenvectors, then it is diagonal form or it is Jordan form and all that actually. We discussed that. We discussed those things in our matrix review class before and all. So let's consider our stability analysis here. First we will consider that the system is let us say it has that the system matrix A has n linearly independent eigenvectors actually. It does have actually. Okay. Then what you have here is that okay, A is nothing but P D P inverse, that is all I can write. So, this is like B is nothing but D now. Okay. So, if B is P inverse A P, so obviously like well this B becomes D here. So, then what you have D equal to P inverse A P. So, if I take P D P inverse, then I am pre multiplying this side by P and post multiplying by P inverse, then it is P inverse A and P inverse actually. Okay. So, this will be identity, that is identity. So, that is my A matrix. Okay. So, A is nothing but P D P inverse actually. So, that is what you are having here. So, A is P D P inverse. The nice thing about this particular form is when I take A square, okay, that A square becomes is easy to see. So, A square is nothing but A times A. Okay. So, A times A is P D P inverse times P D P inverse, and these two will combine to identity. So, what you are left out with is P D square P inverse. Well, I do not know. Okay. So, similarly, if you do this algebra one more time, you will get A cube is nothing but P d q P inverse actually. Okay. And similarly, A fourth is P d fourth P inverse, like that it will continue actually. Where we know that this is n independently, I mean this is n linearly independent eigenvectors. So, obviously, D, this particular matrix D that we are talking about is nothing but a diagonal matrix, where diagonal elements are just eigenvalues actually. Okay. So, that means D takes the form of lambda 1, lambda 2 up to lambda n. This is just written in a compact form out there actually. Okay. So, that is what is written in a compact form, and the P is nothing but eigenvectors. Okay. P 1 is nothing but the eigenvector of the matrix, P 2 is a second eigenvector of the matrix, and we have n linear independent eigenvectors. So, we can write that P 1 is nothing but first eigenvector, so P 2 is second eigenvector, like that actually. So, corresponding to P 1 corresponds to lambda 1, P 2 corresponds to lambda 2, and P n corresponds to lambda n, like that actually. Okay. So, we know that, I mean this is very clear to us. Now, how do we make use of that, let us say. So, we know that this particular solution, okay, solution of the system what we started with, okay, and A is a constant matrix, okay, time invariant system. So, obviously, the solution takes the form of this way, e to the power a t times x 0. Now, e to the power a t, I can expand it that way, that is the definition of e to the power a t. Okay. We have discussed that in the previous class. Okay. We started that as a definition and then formally solved this particular form. When you take e to the power a t times x 0 is nothing but a solution of the system, and hence the solution, and then initial condition got satisfied with respect to x 0 that way. We discussed all that in previous class actually. Now, okay, this I whatever you have here, okay, the second row. Okay, what you are doing here is we are just introducing this term that I equal to p times p inverse. Okay, I just write it that way, and then A is nothing but p d p inverse. That is just that we did that. A is p d p inverse, A square is p d square p inverse, like that. So, we substitute that A is p d p inverse, A square is p d square p inverse, and then t square by 2 factorial, say, like that it will continue basically. Okay. So, what is nice thing, if you see the t square by 2 factorial, all that are scalar quantity, they are not vector matrix, things like that. So, I can put that anywhere I want. So, what I do is this t I just take it and put it here, that means I take it from the right and just put next to d, and then d square by 2 factorial I take it from here and put next to d square by 2 factorial, I mean next to d square. So, it becomes d square times d square by 2 factorial, like that actually. So, what I have after that? I have entire sequence of these matrices that is coming up. It is all getting pre multiplied by p and post multiplied by p inverse. This entire term what you see in bracket is everything is pre multiplied, every term by term is pre multiplied by p and post multiplied by p inverse actually. So, I can take everything p pre multiplication common, p inverse post multiplication common, and then I can have this one actually, right. So, obviously, by definition again, so this is e to the power a t, so obviously, this is nothing but e to the power d t. Okay. And when you have e to the power d t, obviously, these are like a diagonal of that. So, let us see that very quickly. Okay. So, we have d is nothing but lambda 1, lambda 2, like that. Remember, this is like a diagonal matrix. So, what you are doing is e to the power d t. Okay. So, e to the power d t is nothing but I plus d t plus d square t square by 2 factorial, like that actually, d q t q by 3 factorial, like that, that is by definition. So, what I have here, I is nothing but 1 1 1 1 in the diagonal, okay, plus d is nothing but lambda 1, lambda 2 up to lambda n, okay, and then this is t here. So, it will get multiplied with t, everything else is 0, okay. And the second term is something like we have this d square, remember this d is a diagonal matrix, lambda 1, lambda 2, lambda n, all that. So, d square is nothing but lambda 1 square, lambda 2 square up lambda n square, okay, in the diagonal of diagonal nothing, and then you have t square by 2 factorial. So, I can multiply everybody by t square by 2 factorial. So, it is t square by 2 factorial, like that. t square by 2 factorial, and the other terms will be like that. So, if you see all these matrices are just diagonal matrices actually. So, what I have here, if I write one term by term here, the first term will be 1 plus lambda 1 t, okay, plus lambda 1 square t square by 2 factorial, like that. But remember, this is just first element of the matrix. Okay. Second element will be 1 plus lambda, second diagonal element will be 1 plus lambda 2 t plus lambda 2 square t square by 2 factorial, like that, and everything will continue in the diagonal way. Off diagonal will always 0 actually. Okay. So, what I am doing here, I am just taking this d this d out here, okay, and then I am just substituting the d to the power dt by definition, whatever this is. Then I just put I is nothing but 1 1 1 in the diagonal, okay, dt is lambda 1, lambda d is nothing but lambda 1, lambda 2 up to lambda in the diagonal, okay. So, that is all there, multiplied by t. So, all other elements are 0 anyway. Similarly, t square by 2 factorial again I do, and it series will continue actually. Okay. So, this okay. So, okay. So, all right, and this series results in this 1 plus lambda 1 plus lambda 1 square t square by 2 factorial in the first diagonal element, second diagonal element, and things like that, it continues that way actually. So, essentially that is what is done here, okay. And so, e to the power dt is nothing but this diagonal matrix actually, this symbol stands for a diagonal matrix actually, okay. And this P inverse x 0, okay, this whatever you see here, this P inverse x 0, I am defining that as something like C. Okay, so, because remember x 0 is a vector and P inverse is a n by 1 matrix actually. So, the P inverse x 0 is just a vector, and that vector I am defining it as C actually. Okay. So, I have a square matrix multiplied with another square matrix multiplied with a vector actually. So, ultimately the result is a vector which is also x of t is a vector in the left hand side. So, that satisfies that actually. Okay. So, then what we do here? So, if you see this entire series what you see here, remember P is also nothing but this way, this is P1, P2, P3, or right, P is also nothing but P1, P2, P3 like that actually, right. These are all vectors, P1 is a vector, P2 is a vector, these are eigenvectors of a matrix, but they are vectors actually. So, what you have here, the entire solution what you are looking at is a series of column vectors multiplied with a diagonal matrix multiplied with a vector C1, C2 up to Cn actually. So, that entire thing I can rewrite this system in this form actually. Okay. So, if you think a little, and probably I will encourage you to do it yourself maybe. So, this P1, P2 are column vectors, this is a diagonal matrix and there is a C. Okay. So, that remember what is this actually by the way, this series what you see here, what is this? Okay, this is this series is nothing but e to the power lambda I t obviously, right. So, that is the beauty of having a this diagonal matrix and all that. So, this entire series will result in something like e to the power lambda 1 t here, okay, e to the power lambda 2 t here and things like that, e to the power lambda n t here. Okay, that is all it will result in actually. Okay. Because all these series again 1 plus lambda 1 t plus lambda 1 square t square by 2 factorial plus lambda 1 q t q by 3 factorial, all that result in e to the power lambda 1 t like that actually. So, that is the beauty there actually. Okay. So, I can essentially write this, okay, this matrix that I am talking here as P times this one, this diagonal matrix times C1, C2 and all that, you can just see that actually that way. So, what you observe here, this is also called something, this same solution whatever we had here, okay, instead of writing that way we have been successfully, we are successfully writing it this way in the form of, remember Ci also comes from some P inverse x 0 where initial condition is embedded actually, initial condition goes there. Okay. P inverse is a matrix where it may or may not have direct meaning of that, it is this P inverse of this P matrix, where otherwise it is e to the power lambda I t, or lambdas are directly eigenvalues, and Pi's are directly eigenvectors. So, this is actually the Ci embeds initial conditions and inverse of P matrix together sort of thing. And then after that these constants aside, we have the solution in the form of eigenvalues and eigenvectors actually. Okay. So, this solution is something called modal form of solution, because eigenvalue eigenvector pairs are nothing but modes of the system. Eigenvectors are essentially modes of the system. Okay. If you have eigenvector 1, 2, eigenvector 2, things like that, they are essentially system modes actually, and the energy associated with that are given by eigenvalues actually in a way. Okay. Eigenvalue is not directly the energy, but they I mean they signify the energy content actually there. Especially if you have a symmetric matrix, then we know that eigenvalues are real, and in that sense it gives even more meaning actually. Energies are typically positive quantities, so lambdas have to be positive for that. So, system matrix has to be positive definite, all sort of things will start from there. We will not digress so much on that actually. The whole idea is this eigenvectors are nothing but modes of the system, and hence we have this x of t given in this form is called modal form actually. Okay. So, what you conclude from here? C is a constant thing. Okay. Every Ci, what you see, C is just a constant. In fact, Ci is a scalar. C is a vector ultimately. Ci, every element of that vector is a scalar, and then Pi is a vector obviously, but that is still a constant vector. Okay. Eigenvectors as for the constant matrix, they themselves are constant. So, the time varying part is all there actually. Okay. E to the power lambda I t. Okay. And what e to the power lambda I t, it is a summation series. Remember that first term will consist of e to the power lambda 1 t, the second term plus term it will contain lambda 2 t and things like that actually. So, what does it give us? Okay, if I can probably write it here itself. So, this is essentially C 1 e to the power lambda 1 t p 1 plus C 2 e to the power lambda 2 t p 2 like that actually, C n e to the power lambda n t p n. Okay. That is what you are looking at actually, and e to the power lambda 1 t. Okay. What we know actually, e to the power lambda 1 t is essentially e to the power sigma 1 t. Okay, sigma plus j omega. If I write lambda 1, lambda 1 is nothing but sigma 1 plus j omega 1. Then if I write that, then this is e to the power lambda 1 t is nothing but e to the power lambda sigma 1 t into cos omega 1 t plus j sin omega t. Okay, omega 1 t, right, we know that. Okay. And this one essentially you can write it in a different form, you can write in a phase form and things like that. I mean, so what you have here, this particular thing is always bounded, right. It is never going to be, I mean it is never going to infinity, or neither it is going to decay. These are sine cosine terms actually. So, whether the solution will go to infinity or go to 0 is all embedded here, e to the power sigma t basically. Okay. So, if any of the sigma thing, like for example, sigma 1, sigma 2, sigma 3 up to sigma n you have, and any one of that is destabilizing, in other words any one of that is positive quantity, then the solution will certainly go to infinity, right. So, the solution to decay to 0, each of the term has to decay to 0, and for that all these exponential terms that you see here should necessarily decay to 0 actually. Okay. So, that is that's what we mean actually. So, what it tells you is the solution nature depends only on the location of the poles, and it it essentially gives us that if the poles are in the left half plane, then the system is stable, and the one pole in the right half plane, the system is certainly unstable, because that part will go to infinity and everything else will go to infinity because of that. Okay. Alright, so this all happens when n has n linearly independent eigenvectors. So, the question is what happens otherwise? Does it still have that meaning or no actually? So, let us see that. Okay. So, if it does not have linearly independent eigenvector, n of them, then also what we really have, we can reduce this A matrix to a Jordan matrix, is actually a block diagonal matrix actually. Okay. So, what happens, instead of D we should be able to write in the form of J, where J is not diagonal, it is not a purely diagonal matrix, but it is a block diagonal matrix where each of the blocks are J1, J2 up to Jp actually. Remember, this need not be Jn, P is different from n because the blocks, I mean if P becomes n, then obviously this J1, J2 are nothing but simply eigen 1 by 1 eigenvalue matrix actually that way, but otherwise it is J1, J2 up to Jp. Okay. So, A is nothing but Pjp inverse, almost very parallel to what we did here. All that thing what we did here, instead of D we have to write in terms of J basically. J is nothing but the Jordan matrix. So, A square is Pj square P inverse, Aq is Pjq P inverse like that, where J square Jq will all satisfy this equation. Remember that instead of lambda 1 square lambda 2 square, we should be able to write in terms of J1 square up to Jp square, whereas remember that these matrices are actually block I mean they are all this J is nothing but block diagonal matrix. That means these are not necessarily scalar quantity, these are small dimensional matrices actually, each of them can be a matrix by itself actually. Okay. So, but you will be able to write J square Jq like that, and then the analysis also goes in parallel here e to the power 80 times x 0. So, we just do the same exercise what we did before, write I as P inverse, A as P J P inverse this time and things like that. Then we take P left common, P inverse right common, and then again define P inverse x 0 something like C actually, we will do that later. And then this entire solution what you see, this is actually a matrix now, this is not a diagonal, element by element we will not be able to reduce it further, but we should be able to tell that okay, this is nothing but e to the power Jt, right, and e to the power Jt is nothing but diagonal of e to the power J1 t, e to the power J2 t like that actually. What you see here, e to the power Jt is a big matrix actually. That big matrix will also consist of diagonal matrices now, and each of the diagonal matrix will be e to the power J1 t, e to the power J2 t like that actually. Okay. Now, we have to carefully analyze what is this e to the power J1 t and e to the power J2 t, things like that. Up to this the analysis is fairly simple actually. How do you do that? Now, let us say instead of doing every individual thing, I will pluck out one particular j, let us say J1, J2 up to Jp I have, let me pluck out one particular j and call that as j hat actually. Okay. And this j hat can be of R by R Jordan block. Remember, it depends on how many times this particular eigenvalue was repeated actually, that R represents that. This j hat that I am picking out from here will that is associated with this particular eigenvalue lambda, let us say, where the lambda is repeated R times actually. So, the j hat will be a particular R by R block Jordan block actually. Okay. So, this j hat times t what I have here J1 t, J2 t like that. So, j hat times t I can fortunately write in the form of this one actually. Okay. So, okay, what is j what is j by the way, okay, any j, okay, any j hat let us say, okay, this consists of this particular thing, right, we have Jordan form. So, this is 1 1 1, okay, all are 1 in the diagonal, okay, okay, let me write it in a bigger way. Let me write it in a bigger way. So, j hat, okay, that is all we are talking about. Okay. J hat is that particular element. So, j hat is nothing but 1 here, 1 here, 1 here, all the way up to, sorry, not 0, but 1. Okay. These are all 1s here, and then you have lambdas just next to them, lambda like that, lambda. No, sorry, I mean I have done a mistake here. So, that is not the thing actually. Okay. This is going to be lambda up to r times it is repeated. So, this is going to be lambda, okay. And then very next to that is 1 1 1 actually, 1 here, okay, 1 here like that actually, 1 here, everything else is 0, that is the particular thing, this j hat that we are talking about actually. Okay. So, this particular thing I can write it as lambda times I, okay, plus this element which is this 0 0 0 now everywhere 0, and then this is 1 1 1 here. Okay. That is all I am doing there actually. Okay. So, obviously, if I have a t term associated with that, then it goes to there and this will go to there, this is all go to there. I mean that's the t term if I have, I mean this t is a scalar quantity. So, it helps me actually. Okay, anyway, so that is what is going on here. Okay. So, I can write j hat of t as lambda t times I, okay, plus E t, where E is defined as that way. Okay. Now, the beauty part of it is this E matrix what you have here, okay, it is defined as something like I mean this 0 0 0 0 there and 1 1 1 1 here. So, that means this is something called idempotent matrix actually. Okay. That means at some power of this it will go to, I mean it will, some power of it will vanish actually, and if it is R by R matrix then e to the power R will be 0, and we can very quickly see that again probably. Okay. So, let us see that in a 2 by 2 case, let me just show you that. So, suppose you have 0 0, okay, and then 1 0 here, okay, you just multiply with 0 1 0 0 again. Okay. This will happen to be all like 0 times 0 plus 1 times 0 is 0, 1 times 0 times 1 plus 1 times 0 is 0, 0 times 0 0, I mean 0 times 0 plus 0 times 0 is 0, and 0 times 1 plus 0 times 0 is also 0. Okay. And if you happens to be 3 by 3, let us say, so what you are talking 0 0 0 and then you have 1 here 1 here. Okay. So, you have this 0 0 0, okay, and then multiply with 0 1 0 and then 0 0 1 0 0 0, okay. You multiply that, you will again get something like, I mean you can verify this, it will happen to be 0 0 1 0 0 0 0 0 0. So, that what does it tell us actually? Okay. If I have some 1 1 element here, this 1 1 will get shifted to 1 actually, it will go to that corner thing. So, this will result in 1. Okay. So, then there is nothing to shift anymore. So, that the next one will become 0 actually. So, that is a 1 1 shift, it will happen in off diagonal sense, and it will ultimately go to 0. That is the nice part of it actually. Okay. All right. So, coming back to that, this is what we are observing. So, E is like this. Okay. If E is like this, okay. Okay. So, I mean this j hat of t is lambda times t plus I plus E t, and then E is nothing but that. So, E square is just one element of, that is what I just told you. This 1 1 what you see, what you saw here, this particular row, well let me draw that in a better way. Okay. This particular off diagonal, okay, this gets shifted by 1, okay. That is what it happens. This is the, remember this is diagonal here, I mean this is diagonal, this is diagonal, this is one gone. Now, you are having the next one actually. Okay. Now, similarly, this process continues up to e to the power r minus 1, okay, and e to the power r will happen to be 0, and hence e to the power r plus 1, r plus 2, everything will become 0 actually. Now, e to the power r plus 1 is nothing but e to the power r into e. So, if this is 0, this is already 0, then everything is 0 anyway actually. Okay. So, we are left out with this j hat of t is in this way. So, what are you having? We are primarily having a diagonal matrix which will never decay, and we have one more term, one more matrix which will certainly decay to a finite series actually. This is not going to be an infinite series. Okay. This happens to one particular element, one particular e to the power j t, remember that. This can happen, this what you are having here is a block diagonal matrix form of e to the power j 1 t, e to the power j 2 t, like that actually. Okay. So, but this is what it is. So, what you have here now? Now, e to the power j hat of t, that is what you are analyzing. This is this is nothing but, okay, what is another thing actually, e to the power j hat t, okay, e to the power j hat t here is nothing but e to the power this fellow lambda I t plus E t, okay, and this is like e to the power a plus e to the power b. Okay. So, obviously, it is e to the power lambda I t into e to the power E t. Okay. Right. So, that is what we are doing here. Okay. Anyway, alright. So, what you are having here e to the power j hat t, okay, is e to the power lambda t, which is one part of it, okay. Lambda I t is nothing but e to the power lambda t also you can say multiplied by I obviously, but I is not necessary because there is another big matrix which is getting multiplied anyway here. So, this particular thing what you have here e to the power lambda t into e to the power e t, and e to the power e t will now turn out from this fellow this particular series, and this series happens to be 1 plus t square by 2 factorial, okay. Remember that this will result in t basically, okay, e t, remember e t, right. So, e will multiply this particular element will get multiplied by t ultimately, this will be multiplied by t square by 2 factorial, okay. This series will be multiplied by t to the power r, okay, I do not know, this series will be multiplied by t to the power r minus 1 by r minus 1 factorial, okay, right. So, if you see the first row, it is all getting 1 from here, that means it is one element is coming from here 1 times t, so that is t. The second element is from t square by 2 factorial coming from here like that actually. So, the first element what you see here is first is 1 anyway, the second one is t, the third one is t square by 2 factorial like that actually, okay. So, the series is actually I mean this is actually like a triangular matrix, slightly the elements are better placed. So, this essentially like what you have here is actually a diagonal, okay. This is the diagonal entries, okay. And then the next one is t, the next one is t square by 2 factorial like that actually, okay. So, what you see here is next one is t all that, okay. Next one is t square by 2 factorial that way, and the series continues actually, okay. Alright. So, what you are having ultimately here, okay, after all these analysis actually, okay, I can certainly write x of t is nothing but e to the power a t times x 0 is that one we analyzed before, okay, that is what we analyzed actually, and then e to the power j t we have seen that this can be written like that, okay. So, that is that we have written that way, and then we talked about, okay, I mean this series truncates after e to the power r. So, we have to only consider up to e to the power r minus 1, that is where the series is over basically, and if I put them this e to the power j hat t is nothing but that is e to the power this fellow plus that fellow. So, this e to the power this into e to the power that. So, that is e to the power lambda t into e to the power e t whatever happens there, and e to the power e t turns out to be that series, that matrix actually. The first row will be that way, the second one truncates, things like that actually, okay. So, what are we left out is if you just put them together, try to put them, and then this p is nothing but again the same eigenvectors, okay. And remember some of these are essentially now see this some of them are essentially like generalized eigenvector now, where you are talking about Jordan form now. So, some of them may be eigenvectors, and then for the repeated ones you may or may not have independent eigenvector. If you have independent eigenvector, it does not, this issue does not arise anyway. So, you certainly are talking about a case where you do not have independent eigenvector. So, we are actually taking the help of I mean generalized eigenvectors actually, okay. So, this is what you are putting here p e to the power j t into c. So, that again I put it back here, and then this c's and all that whatever this I mean this particular thing that we are defining as c here, okay. This is nothing but c, but c the moment the what you see here c 1 c 2 and all that, okay, here I cannot write them as really the elements of the C matrix. I mean these are all also like partition vectors actually, okay. C can be a big vector, C 1 C 2 up to C p are like partition C vectors actually. But anyway this is like up to P 1 P 2 up to P p, and then results in that way actually, okay. So, what you have essentially, okay, right. So, this P 1 that we are talking here, okay, P 2 up to that is like defined that way. So, if it is R is I mean lambda 1 is repeated R 1 times, okay, then C 1 what you see here, okay, will consist of C 1 1 and C 1 2, C 1 3 up to C 1 R 1. The lambda 1 is repeated like R 1 times basically. So, P1 is nothing but P1 vector, P2 vector up to PR1 vector, where P1 is really the eigenvector, but P2 to PR1 are nothing but generalized eigenvector. That is how it is constructed actually. Okay. So, all this mathematical complexity you have to take care, but the point is ultimately I will be able to write it this way, because e to the power lambda 1 t C1 is nothing but e to the power lambda 1 t, which is exponential again, and then this is a vector, this large vector what you saw here, okay, this essentially all these vectors I can I can expand that, okay, and then put it in this form actually. That essentially comes from here basically. Okay. So, okay. So, this is actually a vector. The first one is a largest polynomial, the second one is one order lesser, like that, the last one is 0th order, this is only a constant value actually. So, but essentially this is just a vector. Okay. So, earlier we simply had a nice vector basically, but these are like some polynomial terms actually now. But the point here is you can do similar expression, this is like for J1 basically what you have done. So, J2, J3 all the thing will continue that way. And what message tells us, the one is we have an exponential term and the other one is polynomial term, and we all know that the exponential term will eventually dominate the polynomial term. So, polynomial can be initially powerful, but exponential will eventually dominate any polynomial term, and that is what we are analyzing. When you talk about system stability, we want to find out the system solution as t goes to infinity. So, we are not particular about this some particular finite time and all that actually. The moment anything that goes towards infinity is our concern here actually really. So, what you are telling here again e to the power that exponential term is predominant, and hence the same result holds good actually. So, e to the power lambda 1 t, again I can write that as this e to the power sigma 1 t plus j omega 1 t, okay, and then I can write that e to the power sigma 1 t into that cos omega 1 t plus j sin omega t and things like that actually. So, this will not decay, but this will eventually decay if the system is stabilizing. In other words, if the sigma values, all the sigma values are negative, that means we do not really care about the omega part of it, that the complex part of the imaginary part of it does not play a role here. The sigma is the real part of it. As long as the real value is negative, that means the system is going to be stable. That is all it tells. But all of the roots should satisfy that. If one of them is 0, one of them is in the right hand side, then that particular part of the solution will go to infinity, and hence everything will go to infinity basically. So, that is what it shows you. So, the conclusion part of it, okay. So, what you are telling here is the nature of the solution depends only on the location of the poles, okay, and all poles in the left hand side the system is stable. If one pole in the right hand side, the system is really unstable. That is all we are telling here actually. Okay. So, now going well, the next question is, if you really know this is the conclusion, it does not really matter whether you have n independent eigenvectors or not or things like that. Once it is a relatively simpler analysis, the other one is a little bit complicated analysis rather, but ultimately the results are same. The results tells us that I do not have to care about the eigen spectrum really, I just have to do like eigen values, and if all the eigen values are strictly in the left hand side, the system is certainly exponentially stable. Okay. And that means the error is certainly going to go to 0 as t goes to infinity. So, that is the result. Now, if that is the result that we know, then obviously this is a control design problem. See, up to this it is analysis, we have analyzed the problem, and then let us say we want to design a control for the linear system now. So, obviously one way to look at the problem is like this, okay. I have x dot equal to x plus bu, okay. This is the system dynamics that I have, okay, what I have here, okay. And then I can assume this u to be minus kx actually, let us say just let me assume that actually, okay. So, simply if I substitute it back here, okay, then I get x dot equal to ACL x, where ACL is nothing but a minus Vk. Okay, that is a CL stands for closed loop. So, the closed loop if I have a control design in the state feedback form that way, then this force system in the closed loop is behaving like like a homogeneous system, where the closed loop system matrix is given like that. So, if I see the eigenvalues of A matrix, that is my open loop poles, but if I have the eigenvalues of A CL matrix, okay, that is the closed loop poles actually. So, even if my open loop poles are I mean some of them are destabilizing and things like that, if I am able to design a proper K, so that the eigenvalues of A CL are all in the left hand side, then I am done actually. So, I really do not have to worry about whether eigenvalues of A are really destabilize, all of them are stabilizing or not actually, all of them need not be, but if I am little intelligent, I mean the system allows me to do that obviously, then I can design a control u equal to minus k x, okay, where k is nothing but a gain matrix, that we will see some of the next I mean subsequent classes we will see how to design a k matrix, that is our design part of it. But once we design a k matrix properly, so that this closed loop eigenvalues are all in the left hand side, then we have designed a stabilizing control system actually, that is the philosophy. Okay. So, we are given a linear time invariant system, we just have to design u equal to minus k x, we just essentially have to design a k matrix, then we know u equal to minus k x actually, that is the formula. Okay. So, that is the whole idea of a stabilizing control design, and we will see that see some of these control design ideas in the subsequent classes. Anyway, so let me summarize some of these in this class. Probably I do not have too much time in this class to study about controllability, observability. We will see that next class. And then okay, this is where we started, the system equilibrium, stable, unstable, all that. And then we asked the question whether the system is stable or not, okay. And without solving this, we really do not have to pick up this A matrix and then try to plug in there and then try to plot it and then try to see, we are not interested in doing that. We just we are asking the question, can we infer the nature of the solution without actually solving this, and essentially the answer turns out to be yes, and is all given by the eigenvalues of the A matrix, whether it is it can be diagonalized or not, it does not matter, it has to be only the eigen value location matters. Anyway, so we carried out this, we took the help of the similarity transformation, and we discovered that any A matrix we can actually convert it to either a diagonal matrix or a Jordan diagonal, I mean block diagonal Jordan matrix, I mean that is either way actually. So, we first took whether we can talk about, I mean if it is possible to diagonalize a matrix, then what is the analysis. So, then we started with A equal to P D inverse, P D P inverse, then A square is like that and things like that. So, then we carried out this algebra and tell x of t is e to the power a t times x 0. So, let me substitute e to the power a t, and then I plug it I equal to P P inverse, A equal to P D P inverse like that, and then I took out this P common and P inverse common, and P inverse x 0 I defined it as C, and then I carried out if it is like this, then this is nothing but P times a diagonal matrix where the diagonal elements are nothing but e to the power lambda I t, times C, and then that essentially resulted in a model form of the system solution, from which we are able to conclude that there is an exponential term here e to the power lambda, but lambda can be complex in general. So, there is a real part which will be like this, there is a complex part which will give me like that, and this particular thing I can this is never neither it goes to infinity nor it goes to 0, this is sinusoidal fluctuating all the time. So, whether the system goes to infinity or not is all given by e to the power lambda 1 t, that is all we are telling, right. I mean this so we are telling if all poles are in the left hand plane, then the system is stable, if one pole in the right hand plane, the system is unstable. Similar analysis holds good for even if there is no n linearly independent eigenvectors, we just carry out this almost the parallel analysis up to a point from where we have to depart, and then this is like J is nothing but block diagonal matrix now, and then each of the diagonal blocks are nothing but Jordan blocks which has a specific form, and then we carried out the similar algebra, and then it tell here is the form that is very parallel to what we did before, but e to the power j t we have to analyze it carefully. So, e to the power j t we wrote it that way and picked out one particular j out of that, and then it all if that is the case, then j hat is r by r plus r by r Jordan block, let us say. that I can decompose it into this form, because one, I mean this lambda 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 is there in the diagonal. Let me pick it out separately, plus Et, where E is an idempotent matrix of order R actually. Okay, so e to the power r will go to 0, and subsequently this series truncates. Okay, and e to the power a plus b is nothing but e to the power a into e to the power b. So, e to the power a is this one and e to the power b is that one. So, this particular thing has helped us in writing this form, e to the power j t is e to the power lambda t into whole all that. Okay. And then we discussed, okay, if that is the case, then x of t I can write it in this form actually, where C1 C2 up to Cp are nothing but a specific structured I mean these vectors and all. C1 can consist of that way, where to the first element is nothing but eigenvector, and all the rest of the things are nothing but generalized eigenvectors actually. So, then I will be able to write it in that way. Okay. And essentially it all gives us the idea that, okay, it consists of one component which is exponential, and the other component is all about polynomial. So, eventually exponential will dominate the polynomial series. Okay. And hence I have the similar result that tells me that if all poles are in the left hand side, then I have got a stable system. If one of them in the right hand side, then I have got a unstable system. Then we just well, how to design a stabilizing controller and all that actually. Okay. So, probably with that I will stop it, but before I stop, also let us discuss a little bit about some other topic here. Let us say last class we discussed let us say e to the power a t. There are various ways of evaluating it actually. So, first thing is e to the power a t, okay, the first one, okay, is nothing but I plus a t plus a square t square by 2 factorial. So, that is the series, that is by definition actually. So, if your A matrix happens to be like idempotent, at some point of time this series truncates, then essentially it gives you the accurate result, otherwise this is always an approximate result. So, we normally do not want to do that, we never know when it will terminate, unless otherwise it is an idempotent matrix of that particular structure, we never know whether it is really idempotent or not actually. There is no standard way of verifying that, at least to my knowledge actually. So, e to the power a t, evaluating that in a series way, first of all we never know whether it is very accurate or not. The second thing is it may be computationally intensive also, we do not know how long you have to keep on doing this, a square, a q, all that are matrix multiplications actually. So, the second term, okay, what we do is second approach, let us say A is reducible to this P D P inverse sort of thing. Okay. So, obviously this e to the power a t, okay, if possible, okay, this is in general it is not possible, but D is a diagonal matrix actually. So, if it has n independent eigenvectors, then it is possible actually. So, e to the power a t is nothing but e to the power well P D P inverse sort of thing. So, well, I just write it that way. So, this is I, so that is nothing but well, let me substitute that as P times P inverse again the same analysis actually what we did there. So, P d P inverse T plus P d square P inverse T square by 2 factorial like that actually. So, I can again take out P here and P inverse there, then all that I have is something like I plus D square by 2 factorial like that, okay, and these are T actually, obviously D square T square by 2 factorial like that actually. Okay. So, what I have here, it is nothing but P e to the power and this diagonal e to the power. So, e to the power lambda 1 t, e to the power lambda 2 t, all the way up to e to the power lambda n t in the diagonal, okay, times P inverse. So, if I have this matrix which is diagonalizable, then I can actually compute e to the power a t that way also, where each of that are nothing but scalar exponentials actually. Okay. Now, we will talk about, okay, let us say talk about another one, the okay. So, what we discussed here is two methods, the first is series, the second one is that one. The third one is okay, e to the power a t is also Laplace inverse of S I minus A inverse. We have derived that previous class actually. Okay. right. So, if you take a simple example sort of thing, let us say a equal to 1, I do not know, 2 probably, and 1 3, okay, and you want to have this e to the power a t, and remember this series may or may not truncate if you just directly put it there actually. So, what you need to do is you just S I minus a, okay, you calculate that way, that is S minus 1 and S minus 3 and minus 2 here, okay, and then you talk about inverse of that. So, inverse of that, and 2 by 2 inverse is rather simple. So, it is like determinant in the denominator. So, S minus 1 into S minus 3, and then okay, it is plus, okay, 0 is there. So, it will go actually, and then this is change of elements in the diagonal. So, that means S minus 3 here, S minus 1 here, and change of sign in the off diagonal. So, that is the Z matrix actually. So, that is what it is. Okay. So, you are left out with these terms. So, what is like S minus 3 will cancel from here. So, I got S minus 1 here, S minus 1 will cancel from here. So, I will got S minus 3 here in the diagonal actually. If I multiply element by element, then I am left out with 1 by 2 by S minus 1 into S minus 3. Okay. So, now I have to take inverse of these matrices actually, I mean these elements. Okay. So, I take e to the power a t is nothing but Laplace inverse of this matrix, whatever matrix I have, okay, same matrix here. Okay. So, I mean these elements are the first diagonal elements are simpler in this case. This particular thing you have to go for partial fraction actually, decomposition and all that. Okay. Then we know, I mean Laplace inverse and all how to take, we know actually. So, that is another way of evaluating this I mean this matrix exponential e to the power a t. Okay. But this is okay provided you have a fairly decent size dimension matrix actually. Otherwise, up to that is fairly okay. Yes, S I minus A inverse, we have also discussed an algorithm how to compute S I minus A inverse last class. But taking inverse of that element by element has to be done symbolically at least. So, here you can use some symbolic software and things like that actually if possible. Okay. There is also a nice idea which tells us let us say fourth actually, that I can actually write it e to the power a t, I can write it as some summation of some C I e to the power some sorry a to the power I t something like that. I'll tell the exact thing next class probably. So, in other words what it tells me actually, not this is not either I here. Okay. What is essentially tells me okay, some coefficient k I or something actually. So, what it essentially tells me here is that this e to the power a t, I can always write it in a finite series, okay, provided I compute these coefficients in a good way. Okay, the exact formulas and all I will probably discuss that next class actually. Okay. So, there are various ways of doing that e to the power a t, which will also be necessary for analyzing controllability, observability like that. Okay. We will study all those in the next class actually. Thank you.